Once we have expressed the propagator in this way, we can return to a statement that I made. I made a statement that propagators are inverses of wave operators. So let's see if that is true. To see this, we have to first review a relationship between the Heaviside theta function and the Dirac delta function. Now, it is easy to show that the derivative of the Heaviside theta function is the Dirac delta function. So let me just show this very quickly. So let me, what is the Heaviside theta function? It's a function which is 0, and then it jumps to the value of 1, and it becomes 1. So if this is x, this is 0, and this is theta of x. This is the Heaviside theta function. So one way of approximating the Heaviside theta function is to take a function which, which goes like this. So what we do is that we take a small neighborhood around the origin, and this neighborhood has some width epsilon, and this is 1. And then what we do is that we define a function such that, so we call it theta, the Heaviside theta function, and it'll be the limit of the function where epsilon goes to 0 from the positive side. And it'll be 0 for the value of x less than epsilon by 2. That is this part of the x-axis. And it'll also be 0 for the value of x greater than epsilon of 2. That is over here. But in between minus x by 2 and plus x by 2, we want this function to be 1 over epsilon times x plus epsilon by 2. So for x between minus epsilon by 2 and plus epsilon by 2. So you should be able to verify that this function gives exactly this curve. So if I now take the derivative of this, then I get d theta by dx, and that's going to give me the limit where epsilon goes to 0 from the positive side. Of course, here I will get 0, and here I will get 1 over epsilon, and here I will get 0. So if I look at this function, what does it look like? It'll look like, a small, around a small interval of epsilon around the origin. This function has a height 1 over 1 minus epsilon. And in the limit where epsilon goes to 0, of course, this function becomes infinitely thin and it becomes infinitely high. But the area of this function remains 1. Area under the curve remains 1. That means that in that limit, this is nothing but the Dirac delta function. So we use this. So we can use this to see if our statement that this is the inverse of the wave operator is true. So let's apply a wave operator on our propagator. So what is our wave operator? We are looking at the Klein-Gordon operator. So our wave operator is del squared plus m squared. So, what is del squared? Del squared is del mu upstairs plus m squared. Because we will have an argument x and y, we want to emphasize that we are taking the derivative with respect to x, that is the space-time point x. So let me just use x as a subscript here. So we want to apply this operator, del squared plus m squared, on d, the retarded propagator, x minus y. So what is the retarded propagator? So, the retarded propagator is given by the theta of x0 minus y0, and then the vacuum expectation value of the commutator of x and y. Now, our function phi of x, is a quantum operator. It satisfies the Heisenberg equation of motion. And from the Heisenberg equation of motion, you can derive the quantum Klein-Gordon equation of motion, which is 0. So we're going to use this equation on the right-hand side. So if you do this, if you use the right-hand side, then use this equation on the right-hand side, then what we will have is that we'll have two terms left. This guy acting on the theta function, theta of x0 minus y0 times the vacuum expectation value of the commutator. And then we'll have a term where, one of the guy acts on the theta function and one of the guy acts on the commutator. And there'll be two of those terms, so we'll have a factor of 2 here. And then we'll have delta mu acting on theta x0 minus y0, contracted with del mu upstairs acting on 0, commutator of phi x, phi y of 0. So now what we see is that this thing only depends on x0 and not on x1, x2, and x3. So from here only x0 will be will contribute. So if I apply one of the x0 using the relationship between the theta function and the Dirac delta function, we get a derivative with respect to t times the delta function x0 minus y0. x0 is t, and then we have 0 and the commutator of phi of x and phi of y. And then we'll have, from the second guy, we'll have another delta function here. So we'll have plus 2 delta of x0 minus y0. And here, this guy will act only on this, and that will give me the, so here we have, this thing will only have the value 0, and that will mean that only the derivative with respect to 0 here will contribute. But the time derivative of the phi operator gives me the pi operator. So we have here the commutator of pi of x and phi of y. And then over here, what we get is that we get the derivative of a delta function times some other function. And we know that by doing integration by parts, we can write this as minus of the delta function times the derivative operator acting on this guy. But the derivative operator acting on this guy will just turn this thing into a pi operator. So we get this, and here we have pi of x and commutator with phi of y, the vacuum expectation value. And so we get basically the same kind of term in both terms. And so if I simplify it, I get a delta of x0 minus y0. And then what do I get? Here I get the commutation relationship, but it's not equal time. But you see that because of the presence of this delta function, any contribution from this commutation relationship, which is not at equal time, will vanish. So we have here, we can write this as a commutator of pi of x, three-dimensional x, at time x0, and phi of y, three-dimensional y, at time x0, and the end of commutator, and the vacuum expectation value. But what is this? This is nothing but minus I, the three-dimensional Dirac delta function, which combining with this now gives me a four-dimensional Dirac delta function of x minus y, and then we have the expectation value of the vacuum, which is just 1. So basically what we are getting is that the Klein-Gordon operator acting on the retarded propagator gives me the Dirac delta function. And this is exactly what we claim, that the propagator is the inverse of the wave operator. Now there's another way to find the retarded wave function, the retarded propagator, and that is to kind of start with this equation of motion and solve it. So what we do is that we take the Fourier transform. So d of r, suppose we didn't know what d of r was, we can write this as a Fourier integral, a four-dimensional Fourier integral, like this. So now d tilde is the kernel. Now we know that the four-dimensional delta function is nothing but d for x by 2 pi to the power 4 e to the power minus I k x minus y. So if I now plug both of these guys into this thing, then we can go to momentum space, and we see that in momentum space, d tilde of k is nothing but I divided by k squared minus m squared. So this is the formal solution to the propagator. But there's a problem with this equation, and the problem is that for values of k squared equal to m, we have a singularity. So we don't know how to evaluate this propagator. And what we're doing here is that by giving the, by specifying, this boundary condition, which is also encoded in, these contour integrals, what we're doing is that we are telling we are specifying how this singular point should be specified. So without the boundary condition specification, there is no meaning to this propagator.